Welcome to this lecture on receptor tyrosine kinases. Imagine your body as a vast, bustling city. For this city to function, its trillions of cellular inhabitants must constantly communicate with one another. Today, we are going to explore one of the most sophisticated and crucial communication systems in human biology. We will learn exactly how chemical messages from the outside world are received, translated, and amplified deep inside your cells to keep you alive. To understand how these receptors work, let us start with a simple analogy. Imagine a highly secure bank vault that requires two separate bank managers to insert their keys and turn them at the exact same time. If only one manager shows up, the vault remains firmly locked. However, when both managers insert their keys and step close together, the locks sync up and a massive alarm bell rings inside. In the human body, receptor tyrosine kinases act exactly like this dual-key security system on the surface of our cells, waiting for specific chemical messengers to arrive. Now that we have a mental picture, let us break down the formal biological name so it makes perfect sense. The word receptor simply means it is a protein acting like a satellite dish, receiving a signal from outside the cell. Tyrosine refers to a specific amino acid, which is a building block located on the inside part of this protein. Finally, a kinase is a specialized type of enzyme. Its sole job is to transfer energy-rich phosphate groups from ATP onto other molecules. These receptors specifically bind to polypeptide hormones, growth factors, and cytokines. Building on that definition, let us look at what actually happens when a signal arrives. When a hormone binds to the outside of the cell, it activates that inner kinase engine we just talked about. This engine begins a process called phosphorylation. It takes energy-rich phosphate groups and attaches them specifically to those tyrosine residues on the inside of the cell. You can think of this as flipping a series of molecular switches. This single action triggers a massive, complex cascade of cellular activities, passing the message deep into the cell's interior. Understanding this mechanism leads us to why these receptors are so absolutely vital to our survival. Receptor tyrosine kinases control the most critical life or death decisions a cell can make, such as whether to grow, divide, or survive. For example, the hormone insulin works entirely through a specific receptor. When you eat a meal, insulin binds to its receptor on a muscle cell, triggering it to absorb glucose and keeping you energized. However, if these systems mutate and stay permanently switched on without needing a hormone, the cell divides uncontrollably. This is exactly how many forms of cancer develop. Since these receptors are so crucial, we need to understand exactly how hormones activate them. In endocrinology, we use the word ligand as the scientific term for the hormone or molecule that binds to the receptor. The relationship between the concentration of the hormone floating outside the cell and the fraction of receptors that are actually bound is highly predictable. By studying this relationship, endocrinologists can determine the fractional occupancy, which tells us exactly how strongly a cell will respond to a given dose of a hormone. To quantify this relationship, we use the fractional occupancy formula. Conceptually, this equation compares the amount of hormone present to the receptor's natural affinity for that hormone. In this formula, Y represents the fractional occupancy, which is the fraction of total receptors currently bound to the hormone. L represents the concentration of the free ligand, or hormone, usually measured in nanomolar units. Kd is the dissociation constant. It represents the specific hormone concentration at which exactly half of the receptors are bound. If the hormone concentration L increases, the bound fraction Y also increases, approaching a maximum of 1, or 100%. Conversely, a high KD means the receptor has a low affinity, requiring much more hormone to activate. Now that we have our formula, let us apply it to a real patient who has just eaten a meal. We are given a blood insulin concentration, our ligand L, of 2.0 times 10 to the negative ninth molar. The dissociation constant, Kd, is 0.5 times 10 to the negative ninth molar. We need to find the fractional occupancy, Y. We chose this formula because it directly relates these three variables. First, we substitute our known values into the numerator and denominator. Because all terms share the same power of 10, we can factor it out and cancel it, simplifying our math. We are left with 2.0 divided by 2.5. Dividing these gives us 0.80. Physically, this means 80% of the insulin receptors are actively sending signals, prompting muscle cells to rapidly absorb glucose. Having seen how the outside of the receptor is activated, let us shift our focus to what happens inside the cell. Once the receptor is bound and activated, its internal portion acts as an enzyme, specifically a kinase. This kinase begins phosphorylating target proteins floating in the intracellular fluid. Just like any factory assembly line, the speed at which this kinase works depends heavily on how much raw material, or substrate, is available. Because the receptor is functioning as an enzyme, its behavior and reaction speed are governed by the standard rules of enzyme kinetics. To calculate exactly how fast this internal engine is running, we use the Michaelis-Menten equation. Conceptually, this formula describes how the speed of an enzyme changes as you give it more substrate. In this equation, V is the current velocity of the phosphorylation reaction. Vmax represents the absolute maximum speed the kinase can achieve when fully saturated. S is the concentration of the target protein, or substrate, inside the cell. Finally, Km is the Michaelis constant, which indicates the substrate concentration needed to reach half of the maximum velocity. If the substrate concentration S increases, the velocity V will also increase, eventually leveling off as it approaches Vmax. If Km is large, the enzyme requires a lot of substrate to get going. Let us put this equation into practice with our activated receptor. We are given a maximum velocity of 120 micromoles per minute, a Michaelis constant of 40 micromolar, and a target protein concentration of 120 micromolar. We want to find the current reaction velocity. We use the Michaelis-Menten equation because it perfectly models this enzymatic behavior. We carefully plug 120 into the numerator for both Vmax and S and insert 40 for Km in the denominator. Multiplying the top gives 14,400 and adding the bottom gives 160. Dividing these yields 90. Physically, this means the receptor is phosphorylating proteins at 90 micromoles per minute, which is 75% of its maximum speed, indicating a highly active signaling pathway. Now that we have calculated the mathematics behind the process, let us look at the complete physical picture. In this diagram, you can see the cell membrane represented by the horizontal lines. On the far left, we start with two inactive, separated receptor monomers. Notice the extracellular space above, where a ligand is approaching. Moving to the center, once that ligand binds, it forces the two monomers to physically pair up into a dimer. Finally, look at the intracellular space on the right. The dimerization has activated the kinase domains, and the curved arrows show them cross-phosphorylating each other. Those yellow circles represent the phosphate groups attaching to the tyrosine residues, creating the docking stations that will transmit the signal deeper into the cell. To wrap up our lecture, let us review the most important ideas we have covered. First, receptor tyrosine kinases are sophisticated, membrane-bound machines that require a hormone to bind and two receptor units to pair up. Second, we saw how the fractional occupancy formula allows us to predict exactly how many receptors are activated by a given hormone concentration. Finally, we learned that this activation turns on internal kinase engines, which use phosphorylation to pass the life-sustaining signal into the cell. You now have a solid understanding of both the biology and the mathematics behind this fundamental gateway of cellular communication.